Prime relatives, right? It's counting the number of prime relatives. Okay, so we have this, no? If we have two prime relative numbers, then A phi n it's equal to 1 modulo n, and an exercise of this is that if you take two numbers, two natural numbers, such that they are relative prime among each other, and you take one number d relative prime to n, to big N, then you take this and such that you take this such that d times d it's equal to 1 modulo n. Yes, like this. No, modulo phi de n. Then what do you have? You will have that, then you will have that whenever you take no matter which number, n1 equals to m modulo d, m power to the d modulo n, okay, like this. The same goes backwards, meaning that mu it's equal to mu1 modulo d prime, because of this equality, modulo n, okay? So this is an exercise. And to prove this, you have to use the Euler theorem. Okay? Okay. So with this in mind, this will be used. This will be used for the RSA method. Okay? So this is the basic theory that we will need. And in what follows, then we will see three methods in this 1.5 hour. Okay? The first one is the Caesar algorithm. So I suppose most of you already know this, but let's just write it. So I will write here. Everybody can see this, right? So when we are talking about cryptography, we are talking about languages, right? Because we are trying to encode a message, right? And in order to write a message, we need a language, an alphabet, no? So let's take an alphabet, like the classic alphabet, let's say. So let's take A, B, C, D, E, F, G, H, I, okay, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, and Z. And C. I could even put more symbols, but I will just put here another symbol that it will be the free space. Okay? So to each letter, I will assign a number. That would be like the natural, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, and 27. Okay? Cool. So, whenever I have a word, I can assign a number to it. So, you tell me your favorite word in the world. Tell me just one word, your favorite word.
Mexico.
Eh? Mexico. I was thinking Pakistan. Okay. I will put just Pakistan because we are in Pakistan, right? So, let's take Pakistan, no? So we take Pakistan, and then its symbols will be, can you tell me, please? So the first one, it will be 16, 01, K, 11, 9, 19, 20, 01, that's a 14. Okay. So now I have a complete word, a number, no? If I give you this number, in principle, that will be already an encryption, no? But it will be so easy to crack, no? It will be so easy to crack because you will say like, oh, let's try to assign numbers to letters, and then you will do like what we have done, no? It's like, and then you do cryptography, no? So, no. Okay, this is like a first principle, right? But then we can do another thing, no? We can just use this modular arithmetic to do cryptography, and then just to put a key, no? Just use a key to encrypt this, no? So we will use a key. Mm-hmm. The key will be something that will help us to lock, no? And to unlock the message, okay? So in this case, the key has to be a number between 1 and 27, no? Well, here I will put 00 because 27 and 00 is the same, okay? So just tell me one number. For example, I don't know, 4, no? Let's say that the key is m equals to 4. And then I will just do the stupid thing, that is to add things, no? So I will have 26, I will add, well, let's put it a little more interesting. Let's say 11, right? Why not? Just to put it. So it will be 16 plus 11. It will be 27, 12, 22, 20, 19, 20, 30, 30, 31, 12, and 15, okay? So many of these numbers are out of my range, so, but I can do the modular thing, modular thing. So 27, I know that it is 00, 12, 22, 20, 30 will be 3, right? 31 will be 4, 12, and 15. Okay? So now I will give you this, no? So if we have two people communicating each other, I will give him this number, but in order him to decipher, he needs to know the key, no? So if I have Alfredo in this side, and I have Bruno on this side, I don't know if you have ever seen some cryptography, but usually they use Alice and Bob. Whenever you see a book on cryptography, you will always see the messenger is Alice and Bob, but it's just to take A and B. So this will be Alfredo and Bruno, because, okay. So what do we need to transmit the message? Because if I only send the encoded message, but I don't send instructions to decipher it, it doesn't work. It's useless, right? So I have to send, Alfredo has to send the message. This will be the message. This will be the message. And it has to, it's a big M. It has to send the message. And here I will put key, K of key. Okay? So he has to send the message and the key. Okay? So that's the information that Bruno needs to decipher that message. Okay?
First line at the end, note of 15 in the 25.
14 plus 11
14 plus 11. Yes, 14 plus 11. It was 25? Yes? Yes, thank you.
Please replace the second line.
Sorry?
Second line.
Second line. This is 04? Yes, please tell me. It's okay?
So basically, she want to ask that how we can come to second line.
How do we come to the second line?
By taking modulo 27.
Yes, by taking modular. You're taking representatives between 0 and 27. You need to have numbers between 0 and 27. Well 0 and 26. If something goes beyond, you have to take the modular representative. For example, if you take n mod 4, so you take 1, 2, 3, 4, 5, 6. And then this will be 0, belongs to 0, 1 to 1, 2 to 2, 3 to 3. 4 repeats and it is 0 again. 5 is 1, 6 is 2, and so on. Okay, so it's repeating. These are the modular integers. Okay? Yes, it makes sense? Another way that you can see it is that exactly, you take the division algorithm, right? So you take m, you take any number n. This you can write it like m cubed plus r, right? And r is between 0 and m minus 1. Well, like this, no? M minus 1. And then the representative will be R. Okay? This is how you get the number that goes in this second line. Okay? Good. So we're encoding this. And Alfredo has to send me this sequence of numbers and the key to decipher them. Okay? And so, how I decipher it, no? I have to do the inverse operation, no? Here, I was taking plus the key. So, if I want to recover the original one, look that this is an invertible operation, no? So I have to take out K, right? So I have this word, this sequence, and then if I take it out, then I will just recover this, no? And then I can recover the word in the usual language, okay? The problem with this is that is the problem of the messenger, no? Because when I send a message, it goes like by internet, no? I send a message, and here's my letter, here it goes, boom, and in the way, there might be people that want to steal it, no? That's what hackers do. They say like, oh, there's a message, let's see what it says, and they take it, and they open it. They try to open it, no? So this is what is called public information. So here, everything is public, no? So if anybody takes this, they can decipher our code really easy. So it's good, but maybe it's not that good, okay? So we need a way, we need a method, we need an algorithm in such a way that we can have public information, but each one of the recipients have private information in order to decipher this, okay? So, and this is where the other two methods apply, okay? So I will just put here, A goes to B, and it sends the message M key, like public information, okay? So, this is the method that are most used, no? And it depends on the factorization. So the second method, this is the Caesar's method. This is the oldest. This has been used by Romans, and they say even by Mesopotamians, they say, no? So, okay, the second method, RSA algorithm. Okay, the RSA algorithm comes from Rivest, Shamir, Yadelman. And it was developed in the 73, 77, okay? So, I will do it by an example, okay? I can write the algorithm, but I think it's better to do it by an example, okay? So, first, we need to prepare the method. We need to prepare the algorithm, okay? Preparation. This is like a recipe, okay? So first, choose two primes. Let's say P equals to 29 and Q equals to 53. For this method, usually they use large prime because this method relies on the factorization of the numbers, okay? So we choose two primes. These are big, but they are not as big, no? And then we will choose an alphabet. To encode, no? So, as we have already translated letters to numbers, let's use the alphabet of the numbers, okay? So let's use the alphabet, let's choose the alphabet, 0, 1, etc. till 9. Okay? So, this alphabet what's the cardinality of this alphabet? It's 10. So we will use set 10. We will use the modular 10. Okay? Then this will be used to, we have to choose, we have to find we have to find K and L such that NK and L to be stretched. This will be used, you will see how this will be used. So in this case, let's use 10 to the 3. Okay, I use this and then I define here N. It will be the product of these two. In this case, it will be 50, 37. Okay? This will be important. Okay? So here we will use, we will need something that it is between this, 50, 37, and here 10 to the 4. So we have 3, K is equal to 3, and L is equal to 4. Okay? So this means that our original blocks of the encoding will be of size 3, no? Original blocks size 3, and destination blocks will have size 4. This 3 and this 4 is this one, this 3 and this 4. Okay? Just stay with me a little more. Okay. So now that we have this, we will need 2 hatch functions. It's 1, 2, 3, 4. 5 hatch functions. This will allow us to move between the mathematics and the language. Okay? So what this means is that we will pass from, remember that this is what it is encoded in our language, okay? And this is what it is encoding the mathematics. So here we have the mathematics and here we have the language, no? Okay, so we are saying that the blocks, we are taking blocks of 3 letters, and these 3 letters we are assigning a number. And to decode it, we will need from blocks of 4 and again, no? Okay, so this is the preparation. This is what we needed for the beginning. I forgot to put this. Okay. So now we will use los 4, 5. Okay, then we will use phi de n. This is okay. Phi de n. This is the Euler function. So remember that if this is a prime, if n is a product of two primes, then in this case it will be, this is p times q, okay? When I take this will be phi of p times phi of q, meaning that it will be p minus 1, q minus 1. Can you remember me who was p and q? P was 29. So p minus 1, it will be 28 times 52, right? Okay. So this will be this number. Okay? Yes. So, I already erased the statement. So here it is the magic. We have to choose, find an exponent. We will need to find E. Phi de n. Okay. So we will define, first is find E such that E and this number, phi de pq, it's equal to 1. So we need to find some E such that with this number it be equal to 1. So let's say it works 47, no? 47, E equals to 47. This will be the exponent, okay? And we need to find the inverse of this exponent, okay? That will be, we need to find D such that D by E it's equal to 1 modulo phi of n. So this is where we are using the statement, the exercise that I left as an exercise, right? So we have two numbers that when we multiply them, it gives us the identity. So this, in this case, the number that can, this solution is not unique, right? Neither this exponent is unique. So let's take D equals to 31. So we have D equals to 31 and E equals to 47. Okay? So this exponent will serve us to encode, and this will serve us to decipher. That's why the terminology. Okay? So, okay. Let's make an example how the algorithm works. So with all of this, we have all the preparation needed. Okay? So I just wrote some random words, but let's see how they work, no? So Lisa space cam space em space Januar. Okay? So first I have to put this in our alphabet. Okay? So L is 12. Just tell me, can you help me a little? 12 I, 9, S, 19, 1, this space, 0, 0, yes, K, 27, 27, no, 11, no, 11, 0, 1, M, 13, 0, 0, I, 9, M is 13, yes, space 09, 00, J, 10, 01, N, it's 14, U, 21, A, 01, and R, 18. Okay? So, here we will use original blocks. Okay? So, here we have a whole chain. Now we have to divide it in blocks. And the blocks have to be divided by this, no? So, it has to be divided in blocks of 3. Okay? 0, 1, 11, like this, like this, like this, like this, like this. There we go. Okay? We have divided in blocks. Now, we have to use our hatch function. Here we have a chains of 3. I didn't say how here I will have, for example, 0, 1, 0, and I will send it to 0, 1, 0 mod 1537, no? The same here. So, in this case, they remain the same, no? Because this is a really big number, so it doesn't change. Okay? So, our blocks will be 120, 919, 010, 010, 011, 011, 300, 91, 300, 100, 114, 210, and 118. Okay? These are our blocks. So, each block, I have to put it to the power E. I will take its power to the E. Remember that E is this guy. E is this guy. Is the encryption. Is the encryption. Okay? So, I will do that. So, I have 100. So, it will be 0734. Can anybody check this? Do you have calculators? If you have a calculator, can you check this? 120 to the 47 modulo this guy, it will give you this, and it goes on, no? 0720 0978 1262 1262. Then we will have 1262 978 1262 1262. This is okay. 00 99, 01, 011, 011. Here it's different. 0, 9. Zero 91, 300, 100, 114, 210, 18. Okay, that's weird. This 011. Here, are we sure about this? According to my notes, this must be a 0. Can you check if it is a 0 or a 3? Okay, 1, 2, 6, 2. So usually here goes 0, 0, 0. And then it goes 0, 5, 8, 9, 0, 3, 4, 0, 0, 4, 7, 0, 0, 4, 9, 6, 1002, 1367. Eh? It's a 3? Okay. So my notes are wrong. So here it must change this one, no? It has to be something else. This must be something else. Okay. Let's see. Let's continue a little with this. We are carrying there a hero. But then this will be our encoded message. This will be our message. All of this sequence. All of this sequence will be our encoded message. Okay? And our public key, and this will be our public key. Okay? So, what do we do now? So, now A here we have A and here we have B. A will send the message to B. It will say M and public key, no? And N. This is what he is sending. Okay? Both of them both of them knows the cipher codings. So now, in order B to decode this, what does he need? What does B needs to decode this? How can we decode it? How can we read it? How can B read this? So, in order to decode it, we will use the exponential to the D. No? That's why it is a D, it's decoding. Okay? When we use D, so we will have this number, each one of these blocks, we will 0734 to the D, modulum 5034. Okay? So, in this sense, he will recover blocks again, no? He will recover 120, 919, 010, 011, 011, Well, here, this is wrong. This is wrong. This has to be this one. Whatever we need to have this here. 091 300 100 114 210 and 118. Okay? So, in this way, we recover the original message. Okay? And this is just because of the exercise that was left as a homework. Okay? This is just using that. So, what's the advantage of this? What will you need to crack this code? What will you need to crack this code? So here you have A, and here you have B. So what Alice is sending, what Alfredo is sending to Bruno, first he sends the public key will be the N. It will send the N and the encoding. Okay? The encoding exponent. And then if Bruno wants to decode this, then he will need to find D, right? But we can find D just by using the Euclidean algorithm in this part. So with this information, Bruno will be able to send a message. In fact, Bruno is not receiving a message. He's only receiving the key. He's only receiving the key. In fact, no? He doesn't, he wants to send a message to Alfredo. Okay? And so what he will do, he will encode like in this sense, and he will send M. He will send the message M. He will send only the message M. Okay? Just like that. He doesn't know how to decode it. Okay? So in this way, Alice, in order to the message M, that we know that it is M, the original message, that this is the original message, and the message is M to the E. No? So we have this. And Alfredo, in order to decode this message, it has to take M to the E and then to the D, M, E, D, no? And all of this modulo N, okay? So as you can see, if somebody intercepts the public key, it doesn't serve if he doesn't have the D. Because this is a huge information, okay? To find D is difficult. It's really difficult because you have to rely on the factorization of primes. You will need to know how to factorize primes. So if you know how to factorize big primes, then you can break this code really easy, no? Because then you could find a D that factors this, no? You will need the factors of N, no? You will need the two factors of N, and then you will need to find this decomposition. You will need to find an integer such that D by E gives you 1 modulo N, and this can be done, but this relies on the factorization of primes, right? So there it is. We have a public key, we have a message, but only B can send message to A, no? If we need that A sends message to B, then B will need to send also a public key, no? And to repeat all this process. Okay? How do you see? It is a little, it is just using arithmetic, modular arithmetic. Okay? So, this is the second algorithm. And the third algorithm that I want to talk you about is called, with this algorithm, is the Diffie-Hellman algorithm, okay? And this is what we will be using mostly. Okay, I will write here. Diffie-Hellman protocol. It's called protocol. So, sorry, questions till now? Do you have any question? Everything's okay? Yes? Okay. So, this is a nice algorithm. I will just put here the main diagram. We have A, we have B, and we will have a public key that is shared between these two. A public key. And with this public key, they will be able to send message to each other. Now, with this public key, they are able to share message in both ways. Mm-hmm. This, for example, the RSA algorithm is the one that you use, for example, to use passwords. No? To use passwords, in this case, this is the RSA. For the RSA, for example, A only verifies the information. It cannot send back information, no? It's like B is us and A is the banks, for example, no? And when we put our password in the ATM, this is the algorithm that it is used there, okay? And here, the Diffie-Hellman protocol is used, for example, in WhatsApp, that we have communication both sides, okay? We have communication in both ways, okay? So here we have a public key. Here we will have a message. Here we have a message in one sense and in the other, and they both will have a secret key. Mm-hmm. A secret key. This is the diagram. So I will erase here. Yes? Okay. Okay. To do this, okay, let's begin. So, preparation. So choose two primes. P, let's say 23, and Q equals to 7. Mm-hmm. So we have, you have to choose just one prime. I will begin again. First, choose a prime number. Let's say P equals to 23, and the two choose a generator. of this is a cyclic group, right? So choose a generator. Let's choose 7, for example. And then to construct the public key. The public key will be as follows. Choose a number A between 1 and P minus 1. Strictly less than P minus 1. So for example, let's say A equals to 6. So the public key will be G to the A, that in this case is 7 to the 6 modulo 23, that in this case it is 4. It's the same that 4. Okay? The secret key here is A. That the secret key is A equals to 6. Okay? So we have the public key is this, and the secret key is this another. Okay, so what do we have now? We have the public key of Alice, and so the complete public key, no? Public key. The prime number, the generator, and the generator today. So according to what we have is P is equal to 23, right? So it will look 23. G is equal to 7, and G power A, it was 4. Yes? Like this. Okay. This is the public key. And now Bob has to choose also a secret key, no? Sorry, B chooses a secret key, likewise, no? For example, just as Alice did, no? B equals to 3, for example, no? So the public key of Bob will be GB. That it means it will be 7, 3. This will be 21 mod 23. And this is also public, no? So the shared secret key will be C equals to G A to the B. That will be 4 to the 3. That means 18 modulo 23. Okay? So let's see how it works. Let's see how it works. Okay. So with these ingredients, now we are able to send a message. Let's see how it works. Okay? Usually we have to split to have the chain, etc. But just now let's look how it works mathematically. No, just like to a number. Okay. So let's put a message. No. Let the M be the message in set P. For example, we need something that be less than 23. So let's put M equals to 7. So the encoded message will be given by M times C. Recall that C is this, that it is helping us to encode the message. So this means that our message will be 7 times 4. This is modulo 23. This is modulo P. Okay? So I'm wrong, right? Because this should be C, it is 18. Like this. 7 times 18, it is 11 mod 23. Okay? So Bob Bruno, B, I will just put B. B sends the following message. He will send G to the B, M. Okay? This is what Alice will receive. So this means that Alice will receive 21, 11. Okay? 21, 11. So how Alice can decode this message? How Alice can decode this message? So Alice decodes in the following. So we are encoding, we know that M is equal M times C, right? So in order to get little m, we will need to multiply by the inverse of C. It's like simple, right? We need to, so we will need to find who is C, no? But we know that C is G to the A, G to the B. But Alice already knows G to the A, right? And in fact, Alice knows A, and now Alice knows G to the B. So what do Alice need to know to find C? So Alice receives G to the B, and Alice knows A, right? So she only has to take the power to the A and recover C. right? Because Alice already knew A, she chose it. So what she does is just like that. She takes G to the B, she takes the power to the A, she recovers C, and in order to have the original message, what she has to do is multiply the message, the big message, M by C inverse. Right? So she does that, no? And then she recovers, of course, here. What she does is she takes 21. What was A? A was 6. So she takes this to the 6. You have to convince that this is exactly the same, no? This is 18. Okay? And then, with this, what is the inverse of 18 modulo 23, sorry? So M will be 11 times 18 inverse modulo 23, and then you recover 7. Our original message. Okay? And this go backwards. This go in both sides. Okay? So it seems complicated, but it is just that you have to practice. Okay? So that's what I would like that we do right now. Okay? Here I choose 23, but maybe 23 is I think is fair enough, no? Or we can use a smaller number.
Why did you choose the prime number?
Why are we choosing prime numbers? Here, in fact, you don't, for this algorithm, you don't need a prime number by itself. In the RSA, it is, you hardly rely on prime numbers, but here you don't really need prime numbers, but it makes you easy to choose this public key, no? Because when you take G to the A, you need this coherence, no? G to the A and this other, no? But in fact, it just makes easier the calculations and harder the algorithm to break. But in fact, you don't need prime numbers by itself, no? Yes, in fact, you don't need. In this algorithm, you don't need prime numbers. No? No. You are not using prime numbers anywhere. You are using modular arithmetic. And in fact, what would you need? When you look at this, what will you need to break this code? So what do you need to break this code? What is the public key? The public key here is P, that in fact you don't need to be a public G and GA, no? This is the public key. Remember that P is the modulo that you are working on. G is a generator, and G to the A is the key that is using either Alice or either A or B, no? This could be GA or GB. This is what you are using. And when you send a message, this is sending the message GBM, and this is sending the message MC, and this is sending the message GMC. Okay, so let's try to do it by yourself. No, ensemble yourselves in couples, and send one message to the other. Okay. And we will use 10 minutes, and then a random couple will pass to the blackboard and explain the procedure. Okay? Yes? Yes. See? Okay. So, just begin to work. So, do you want that I give you the numbers? Okay. Let's use so let's take P equals to 23. Let's take the same. Well, better. Let's take P equals to 27. So we can take any letter of the alphabet. Okay? P equals to 27. Let's take P equals to 27. And A and B, you choose it. No? A and B, you choose it. But be careful. In order to this to work, you need to choose a generator of set 27. This is no longer, this is a cyclic group, but not all in this case, any number below 23 is a generator. In this case, you have to look which are the generators. Right? In 27, not all the numbers are generators. Or maybe we can put let's put 31 is prime, right? So let's put 31. Okay. So I will, it's easier for you, okay? So let's put 31. Then you have to use a generator. You have to choose a generator. You have to choose your secret keys. Each one of you have to choose a secret key. And then you have to send the message. The message that you have to send is P. Yes? You have to send the letter P to the other one. Okay? Yes? Okay.